Okay, hi everyone. Welcome to our last video, our last lecture for the semester. In this video, the goal is to see how do similar objects relate with respect to areas and volumes. That is, if I scale up an object, how do the areas change? How do the volumes change? That's the exploration for today. And I'm going to start with this motivating example. So suppose we have a box with a width of 2 inches, length 3 inches, and height 4 inches. In other words, we've got this rectangular prism. And I want to find the volume in the surface area. So I've drawn the net for this same shape. So you can kind of see this is the left face here. This is the front. Whoops. There we go. This is the right. This is the back. And you can kind of fill in everything else from there. So how do we find volume and surface area? So these are, by now, things that we've practiced a few times. In fact, we've taken even learning outcome quizzes on them. So you've had to study this a bit. To find the surface area, there is a nice formula that we actually found for surface area, but let's just do it explicitly. The surface area is just finding the area of this two-dimensional thing. So there are two rectangles of dimension 3 by 4. So those each have an area of 12. So that's that 2 times 3 times 4 is these two. I've got two rectangles that are 2 by 4. So each of those contribute an area of 2 times 4. And then I've got two squares that have an area of 2 times 3. So I know I said I'm not going to use the formula, but what I just talked through really is the formula for this rectangular prism. So just thought I would point that out. Okay, so how does this all work out? This gives us 12 times 2. This gives us 8 times 2. And this gives us 6 times 2. And so at the end of the day, we end up with 52 square inches. Okay? So now let's find the volume. In the volume for rectangular prisms, we have the formula. It's the area of the base times the height. So that's 2 times 3, which is 6 times 4, 24 cubic inches. Okay. So that's just stuff we learned how to do all of this in 13.2 and 13.3. So this is stuff we already know. So let's suppose now that we scale the box by a factor of 2 so that the new box is similar to the old box. And when I say similar here, I do mean this mathematically similar. That means that the shapes are the same, I've just scaled it. It's like it's like a model box or something like that. What is the new volume and area? So I thought we would start off by trying to figure out what the new dimensions are. So if I scaled this box by a factor of 2, I'm going to double the width, the length, and the height. That's what it means to scale. I have to scale all the dimensions so that everything's still proportional. So that gives me a 4, a 6, and an 8. So do make sure you believe that those are that's the correct way to scale these things. Okay, so in that case, this is now the new net for this shape. And I guess I didn't label this one above as well, but that one should be a 4. I'm going to go back up and label that for the final ones. This should be a 2 here. Okay, so let's find the surface area and the volume again. So the new surface area We've got two rectangles of area 6 times 8. We've got two rectangles of area 4 times 8. And we've got two rectangles of area 4 times 6. So this one is just a little bit trickier to compute in our heads, but thanks to me doing the computation ahead of time, the answer is 208 square inches. Okay, for the volume, we again have area of the base, which is now 4 times 6, times the height, which is 24 times 8, and 24 times 8 works out to be 192. Okay, so how can we use the scale factor to relate the volume and surface area of the two objects? So let's do like a little table before scaling, after scaling, and let's record the volume and surface area. So we just got that the volume was, oh, by the way, units are important, right? Inches cubed. There we go. So the volume after is 192. The surface area after was 208. And then our surface volume and surface area before and after, this one was 24. The first one was 52. So my question is, how can we compare these two together and these two together using the scale factor? So this is kind of vague, but there's a reason why this is an example and not a problem. So how are we going to relate these things using the scale factor? Well, how do the dimensions of the original objects relate using the scale factor? I go from something that has 2 by 3 by 4 and I get 4 by 6 by 8. How are those dimensions related? Well, we scaled everything by 2, and so all those dimensions doubled. Scaling things means I just double things, right? So we might ask, is that the relationship between these things? Does 208 equal 52 times 2? The answer is no. It's 104. But you might notice 104 is exactly half of 208. So if I multiply by 2 again, I'll get another 2, and then I'll get 208. Okay, so it looks like 52 times the scale factor squared gives us our surface area. Let's see if the same thing happens with volume. Does 192 equal 24 times 2 squared? So that right there is 24 times 4, which is 96. So not quite, but again, I noticed that I'm off by a factor of 2. If I multiply this by 2, 96 times 2 is 192. So in fact, if I make this 2 cubed, I get this. And so notice this really interesting relationship, that to go from the surface area of the original to the scaled version by a factor of 2, I don't multiply by 2 one times, I have to do it twice. And that 2 should feel right because we're talking about areas. Areas are like squared units, right? On the other hand, when I'm going before and after for volumes, when I scaled by 2, I don't scale the volume by 2 one time, I multiply it 3 times to scale the volume accordingly. And again, that 3 kind of makes sense because cubic units have like a cubed in the exponent of the units, right? We've got cubic inches versus the square inches for area. And so in fact, in general, if object 1 is similar to object 2 with a scale factor of k, that is, I can scale object 1 by a factor of k to get object 2, then this is what happens. The lengths will scale by a factor of k, the areas will scale by a factor of k squared, and the volumes will scale by a factor of k cubed. This guy right here, we've known. This isn't new. This is just what it means to scale. This is what similarity is. This is me scaling the picture of that silly cat by a factor of 2. These two things, those are new. These are the things that I just kind of unraveled for you in this example here. That when I want to take the surface area of an object and its scaled version, and I want to relate them, I've got to square the scale factor versus cubing it for the volume. So what I'm trying to tell you here is that this is a relationship that's always true. And we can use this to find some pretty surprising, we can say some pretty surprising things using this. So let's start with this one. How are the areas of ABC and ADE related? So both of these are isosceles triangles. Now, I did not give you the heights. Technically, because you guys now have the Pythagorean theorem, you could figure out the height and figure out the areas of these two triangles. But I want you to not do that. I want us to not do that, rather. Oh, and also, if I'm going to call these ABC and ADE, I may as well actually have labeled them. There we go. So how is the area of these triangles related? Well, recall from stuff in 14.6 that what do we already know about these triangles? Remember, they have an angle in common. These sides are meant to be parallel. And so by the parallel postulate, these angles will be equal. Those angles will be equal. And so by angle, angle, angle similarity for triangles, we know these are similar. So I'm not writing out all those details. That's what we just talked about in 14.6. Hello everyone, today we're talking about 14.5, similarity. Sorry, some audio just started playing randomly on my computer. Not really sure how that happened. Okay. Cool. So these triangles are similar. So how am I going to relate their areas? Well, in light of what I just talked about up here, it seems like if I can figure out something about the scale factor, if I know what the scale factor is, I can find a relationship between how the areas of two similar objects will scale. Okay. I'm hoping everything's okay. The computer just freaked out on me. This is the second time this happened. I'm going to hope for the best here. So let me maybe start over explaining what I said in this example so far, just in case I lost that footage. So we wanted to show that relate the areas of these two triangles. These triangles are similar because of the same arguments from the last section. Both triangles share this angle. These two sides are similar, so the angles are equal by parallel postulate. So angle, angle, angle similarity says that the triangles are similar. And now I want to somehow use the fact that I know how areas scale if I can figure out the scale factor. So can I figure out the scale factor? And the answer is yes, because while the smaller side length is 2, I can figure out this longer side length to be 6 inches. And notice that the scaling factor k is going to be 6 over 2 equals 3. The bigger triangle is 3 times the size as the smaller one by using this scale factor here, because the side length of 2 is scaled by 3 to get this longer side length of 6. Okay, great. So now what? Well, if k is 3, I know how to relate the areas of these two triangles because areas scale by a factor of k squared. So what this tells me is that the area of ABC has to be scaled, so that number times 3 squared has to be the area for ADE. And so that's the relationship between the area of these two triangles. The area of ABC or the area of ADE is 9 times the area of ABC. So that's kind of a useful thing. And it's important to note that just because I triple the lengths of a triangle, that doesn't mean I triple the area, right? In this case, it went to 3 squared. In fact, this idea shouldn't be overly surprising to you if you remember our dimension analysis stuff. If I have 1 foot is 12 inches, that doesn't mean 1 square foot is 12 square inches. It meant it was 144 12 square inches. That's kind of why we should expect this to square. And the same idea holds for the cubic inches or the cubic volume stuff. Okay, so that was kind of a more maybe, uh, I want to say philosophical, but that's not the right word. This is like a more maybe nuanced situation that like, why would I maybe care about this? So, I mean, you could care about if you knew how much, if this was like a farm and you knew how much manure you needed for this thing, then you want to know how much more manure I'm going to need for this bigger area if I do something to make my farm bigger. There are ways that we could make this more practical, but there are other ways where knowing this stuff can be really practical. So before building a full-sized aquarium, a construction company builds a model with a scale of 1 inch to 5 feet. So again, I am not saying 1 inch equals 5 feet here. I am saying that is a scale. Like think about a map. They estimate the model has 20 cubic inches of space for water. What will the tanks of the actual aquarium be able to hold? Okay, so how do we go about this? So we can think about the scale here as telling us our scale factor for the actual um, model. And to do this right, we want to make sure, I've mentioned this several times in the prior section and or sections, that we want our units to match if we're going to especially do the scale factor method. So our scale is really 1 inch to 60 feet, right? Because, 60 inches. Because in every foot there are 12 inches. So 60 is 5 times 12 there. Okay? So this means the real aquarium or rather the scale factor then is 60 to go from the model to real thing. So if the little toy model holds 20 cubic inches of water, then we can actually find how much water the real aquarium will hold because 20 cubic inches is the volume. I have found my scale factor, and I know that to go from scale factor to volume, or sorry, to use the scale factor to convert volumes, I cube my scale factor, and then I um, multiply the number that is my volume. So at the end of the day, this ends up being 4,320,000 cubic inches. Okay, that's kind of a big number, but remember, this is in cubic inches. I'm totally fine if you leave the answer here, but just for reference, using some dimension analysis, I can deduce that the square foot or cubic footage is 2,500 cubic feet. So the way I got this number is by dividing this number here by 12 cubed because I'm converting a cubic inch to a cubic volume. Okay. So either of these answers here are acceptable. Okay. So that's all there is to this problem. We use the fact that we know how to convert volumes given a scale factor because we have this really nice relationship that volume scale by a factor of k cubed where k is a scale factor. So in this setting, since we know the volume of the little toy model is 20 cubic inches and we know the scale factor is 60, then yeah, we just apply that rule. So this is really nice because like this is a really practical thing, right? Like we could imagine a company is trying to figure out how much water their big full scale model of their aquarium is going to need. And they already know how the small version, they can easily calculate this for the smaller version. And then they can use the fact that they know how this principle works to find how much volume works in the bigger one. So I think this is really nice. Okay, so I now want to talk about how we compare weights of similar objects. Let's say I have two objects that are similar and I want to, like, let's say I have like a bigger model of something and I want to figure out its weight. Sorry, you can probably tell I'm a little distracted. There are new people coming into my apartment right now. Okay, let me maybe start that sentence over. I got a little distracted. So here we showed how to find volumes of a converted. Wow, I'm still distracted. I'm very sorry. I think we're good on this example. So I now want to talk about how to compare weights of similar objects. You probably just heard the dog as well. Okay, so how do weights compare? So it's reasonable to associate the volume of an object with its weight because, you know, if you have like a big tank, we actually kind of talked about this before with capacity. If I've got a big tank, surely if I make the tank even bigger, let's say this tank is full of water. If I make the tank bigger, I also expect the weight to get heavier as well, right? In particular, the volume is how much space is inside and the weight is how heavy the stuff inside the box is. So it works out that we also can convert weights in the same way that we convert volumes, and that's the right thing to do. That is, I can multiply by the scale factor cubed to weights, and that scales things correctly. And this can be useful if you're like someone that's trying to approximate weights of things that no longer exists. So let's check out this example. An adult alligator can be 15 feet long and weigh 475 pounds. Someone finds dinosaur bones and deduces that it was a creature proportional to an adult alligator, except the length was 35 feet. So how much did this dinosaur weigh? There's no way we could actually do this. First of all, even if the dinosaur exists, getting it to comply with us and getting it on a scale and also finding a big enough scale is kind of not very practical. So how could we do this, especially when the dinosaur no longer exists? Well, we can use the fact that weights scale in the same way that volumes do when we know what the scale factor is. So what's the scale factor here? Our adult alligator is 15 feet long. The dinosaur, which is proportional to the alligator, which is important, is 35 feet long. So our scale factor, what we have to scale the alligator by to get the real lengths, is 35 over 15, otherwise known as 7 over 3. Okay, and you can check that if you take our scale factor and multiply it by 15, you do indeed get that length there. So it really does work out to be our scale factor. So then the weight of the dinosaur is 475 times 7 over 3. And how do we convert this weight? Accordingly, we have to cube the scale factor. And now this is the weight of the new dinosaur. And I know that if I don't actually give the number, it won't really give us like a satisfactory conclusion to this, right? So the number works out to be, whoops, there we go, approximately 6,034.2. Or you and sorry, if you're like an archaeologist or I guess archaeologists study human history, so whatever, paleontologists, this is not important. Whoever looks at bones for old dinosaurs and are trying to figure out like how big were these creatures, how heavy were these creatures, this is a reasonable way that you could go about doing it if you can find something that is a smaller scaled version of the object you're dealing with. So in this situation, we use the fact that we know how much an alligator weighs to find how much a bigger dinosaur weighs. And in this example, we use the fact that we know it's easy. We already know how much water fits inside of our tinier model to find how much water would fit in the big full-sized aquarium. So those are two pretty nice applications of this. And now I want you guys to have a chance to practice. Try out this problem, maybe spend about 5 minutes. So this problem is actually based on a real thing. In Aurora, Colorado, there is a 16-foot tall chair, and it's similar in proportions to my chair. This part of the story is a little made up. So my chair is 4 feet tall, has a surface area of 8 square feet, and weighs 20 pounds. So if this is true, I claim that you can figure out the surface area and weight of the large chair. without needing to go find the chair and do stuff to it. So pause for 5 minutes, try to use all the tools that we've talked about. Okay, so before I do this, I want to again emphasize like how useful these tools are. Imagine you were next to this chair. This chair is 16 foot tall. So I mean, I know we're all different heights in the class. I'm about 5'7". So let's say I'm like, let's just like say I'm 5 feet instead. That's a third of the height. That's like how tall you would be in comparison to the chair. That's kind of ridiculous. Could you imagine having to come up to this chair and calculate the surface area? You would need a little ladder to be able to climb up it and stuff like that. And how would you even go about weighing it? Again, this kind of goes back to that prior example I did with the dinosaur. The nice thing is, if you want to find things like the weight, volume, and surface area for really big objects, that might be really impractical to do and really hard. But if you can find a scaled version, it might be easier to find that information, and then you can use our conversions. So first, scale factor, right? What's the scale factor? Since the height of the big chair is 16 and the height of my chair is 4, the scale factor is 4. This means that the surface area for the big chair is going to be the surface area of the small chair times the scale factor squared, which is 8 times 16, which is 124. Or wait a second, sorry, 128. And the volume, or sorry, we're not doing volume, and the weight, remember, how do we convert the weight? If the weight of the chair is 20 pounds, then I can take the scale factor and cube it, and that is how we convert things for, wait a second, that can't be right. Okay, this makes more sense. Just kidding. Okay. Sorry, I was having an argument with my calculator. Okay, pounds. By the way, oh, and units, right? We need units. So this is square feet. There we go. So 128 square feet is the surface area of the chair, and 1,280 pounds is the weight of the chair. Okay, there we go. So I know this was maybe like a little bit of a sillier problem, but I thought it was cool. I have definitely seen pictures of like these like super large chairs. Apparently this is like a very common roadside American thing. Like if you Google large chairs America, there are like tons of ridiculously sized chairs all over the country. And this is like a cool way of saying that we can actually probably figure out things like how much they must weigh and how tall they must be in comparison by comparing them using similarities and proportions to something we have in front of us, some smaller version that we can easily compute these things for. So that's really it for the section. The big point of this section was to understand this relationship, that when you're scaling an object by a factor of k, lengths will scale by k, area scale by k squared, and volume scale by k cubed. And from that, I think these problems are like, at the end of the day, they aren't too like sophisticated. It's just understanding which rule to use. Right? All the work on these problems is very short. The hard parts, I think, is figuring out what the scale factor is and then knowing which thing to use, like whether you're converting an area or a volume. I do want to scaffold problem 4. Problem 4 is a little bit tricky, but I think with a little bit of scaffolding, it'll be doable. And since the homework set, I think, is only about 5 problems anyways, yeah, I'm not too worried about it. So let's say you have 3 pounds of clay, which weighs about 150 pounds per cubic foot. And let's say we also know that marble is 175 pounds per cubic foot. Let's say I wanted to take my 3 pounds of clay and just turn it into marble. Let's say I had a little tiny sculpture made of clay and I want to know if I had instead made the sculpture using marble, how would the weight change? And this is my claim that 3 pounds of clay equals 175 over 150 times 3 pounds of marble. If you are curious, that works out to be about, oops, wrong pen. This works out to be about 3.5 pounds, which makes sense. Marble is heavier than clay, so you should expect this number to be smaller. So why does this make sense? Why is this what you should do? Think about dimensional analysis. We're saying for every 150 pounds of clay, that same shape would weigh 175 pounds if it was marble. So we can think about this as a dimensional analysis problem. 3 pounds of clay can be converted into pounds of marble by multiplying by this conversion. Every 150 pounds of clay is 175 pounds of marble. This is exactly as if this was like 1 foot on the bottom and 12 inches on the top. We're really doing the same kind of things. And so the units cancel and we get our answer. So that's going to help you for problem 4. Problem 4 is another one of these similarity problems. But if you just were to do, if pretend like you didn't know this thing I just told you, you could do the problem as is using the same techniques that I did in all these problems. But if you just do it blindly, what you're going to do is you're going to find the weight of a scale model of a sculpture. So sorry, maybe for context, the problem is about a sculpture made of clay in a scale model, and you want to make the big thing out of marble. So when you do the process, you end up finding the weight of a full-sized sculpture, but made of clay. You then have to do one more extra step to convert it to marble, which is what I've done here. So I'm hoping that what might be best is for you to, you know, don't worry about this too much now if you don't really get what I'm trying to say. It might make more sense in the context of the problem. Okay. All right. That's it. That's our last section. That's it. You have learned everything there is to learn about this class. Very good job. Hopefully this section's okay. I'm hoping this section was on the shorter side, but I think every time I say that, the videos come out to be longer. So hopefully I didn't jinx it. Hopefully this was helpful. And let me know if there are any questions about this. I'm a little worried right now about this problem right here just because I was getting distracted with a lot of sounds going on outside, but hopefully the explanation was clear, or at least the work was clear enough to follow. All right. Thanks, everyone.